So we have a triangle ABC. Oh, this one's kind of interesting. So BD is equal to CE. Let me use my compass tool for this. Where's the compass? BD is equal to CE. All right. Let O1 and O2 be the circumcenters of ABE and ACD. All right. So, oh yeah, there's like a lot of circles in this question. So ABE and ACD. So okay, so we want to show that the circumcircles of ABC, ADE, and AO1, O2 have a common point. So this point right here, we want to show they all meet at this one point, which kind of makes me think of the power ratio lemma. We want to show, yeah, there's a bunch of different ways to think about it, but I feel like the power ratio lemma might just crush this problem. Let's see. So we want to show that D and E have the same, if we take the ratios of the powers with respect to A01, O2 and ABC, we want to show that they're the same. So basically, we want to show AD over AE is the ratio of the power of D with respect to A01, O2 and the power of E with respect to A01, O2. I wonder if, is that obvious? Yeah, I think it is obvious. I think the power ratio lemma kind of trivializes this problem. In fact, I feel like you can probably generalize it more. But I'm going to write it out. Yeah, the power ratio lemma, it's so powerful. It can just crush so many problems. So we want to find the ratio. Hold on just a second. Actually, now I'm not 100% sure about that. Well, no, it's kind of like, I mean, really, we want to show DF is equal to EG. So basically, we want to show B and C have the same power with respect to that circle. Now I'm just getting confused.
Is that point the midpoint of arc BSE?
It could be. Let's see. Yeah, looks like it.
We can try proving this separately for all the 4 points. I mean, assume the midpoint to be M and then prove that it's cyclic with
With all three
two
circles,
yeah,
or with the other two, I guess, right? That's probably
other two.
solve it. So I can show that it's cyclic with D, E, and A. I'm just saying how to show it's cyclic with O1, O2, and A.
Here it should be cyclic with D and A because of the spiral similarity, which takes ADE to ABC.
Exactly. So yeah, for that reason, it's cyclic with A, D, and E. Let's see if we can show it's cyclic with A, O1, and O2. Like all the points. Exactly. Yeah, Hakan, what you're
Yeah,
saying.
AO1. This looks like two of them are parallel.
Are you saying this is like a rectangle or a
No, I think AH should be parallel to O1.
Okay. I wonder if it's a
I
rectangle.
don't.
Oh no, it's not. Yeah.
No, it's a trapezoid.
Yeah, it's a trapezoid. No, I'm sorry for yeah. But yeah, we want to show AH is parallel. All right. How can we show that?
If we let O be the center of the circle ABC, then I think O1 equals O2.
I'm not sure. Sorry. Where's O? Trying to find where O is. Huh. It's weird. Doesn't see the right circle. Center. Oh no, that's not. I want center K. What? What? Okay. Let's see. It is hidden. Ah, there we go. Yes. So there's O. And you're saying O01 is equal to O02. Yeah, I think that would follow by.
Yeah, I think we can angle chase down AO01.
A001. I wonder if O1F is equal to O10, or let me try something. No, it just looked like it. O102.
No, I angle AO01.
A001. Okay.
It should be equal to HOO2 because we are trying to prove AHO1O2 as trapezoid.
Okay, so we can try to show A001 is H002. I think that would prove it's a trapezoid, right?
Actually, A001 looks similar to BEC. I think that's an angle chase.
A001 is similar to BEC.
Yeah.
Hmm.
And yeah, similarity proves that O1 equals O2.
Okay. So I'm just trying to think about this. So all right. Once we know O01 equals O02,
I think that would be an angle chase because we also know that OA equals OH.
but even if we know AH is parallel to O102, would that be enough to show that that is cyclic? I guess is kind of what I'm thinking. So if we knew that they're parallel, that would be a step.
Yeah, that would be enough because we are also proving that O1 equals O2. That would imply A01 equals HO2 by
That would
congruent
mean,
triangles.
okay, so yeah.
Yeah,
Okay.
basically proving A001 similar to BEC finishes in, and that's an angle chase.
Okay. All right. So I'm going to start writing this up. So let H be the midpoint of arc ABC. Yes. Okay. So I'll start out like that. Yeah, I'm going to hide F and G. And then AHDE is cyclic by the spiral similarity. Let me see if there's like a way. So yeah, I mean, HB is equal to HC. Yeah, like I have one proof in my mind. I'm just trying to think of the best way. So, so like triangle HDB is congruent to HEC, and we can prove that because BD is equal to CE, HB is equal to HC. I'll just write that whole thing out. So triangle HDB is congruent to triangle HEC. So that means that HD is equal to HE. I mean, yeah, by spiral similarities, where oh, actually, I can just say this. So that means that angle HDA is 180. DB, which is 180 minus HEC. And so that means ADEH is cyclic. All right. Oops. And then we want to show A0102H is cyclic. We know OA equals, we know O lies on the perpendicular bisector of AH. If we can show it's also on the perpendicular bisector of O102, that would solve it. So we want to show A010 is similar to BEC, as you mentioned. So yeah, I'm just thinking how to do the angle chase here. So we have, let me write this out. Angle O1 AO is equal to angle BAO minus angle BAO1. And then we can write each of these in terms of, so BAO is 90 minus angle C. And BAO1 is 90 minus angle BEA. So that's equal to angle BEA minus angle C, which is simply angle CBE. If I have this all right. Yeah. Wait, BEA minus CBE. Okay, so that's one of the angles. And then for another angle, I think A001, is that the other angle that you saw?
Yeah, that angle should be, I mean, A001.
Oh, because 001 is
basically
001
tried to use symmetry.
Yeah, so the angle between AO and 001, I'll write it like this. That's basically 90 minus the angle between AO and AB, because 001 is perpendicular to AB, right? And the angle between AO and AB, that's 90 minus I don't know if I'm doing this right. Let's see. Something, I think I might have gone wrong somewhere. Oh no, that's right. Yeah. So let me do this. All right, so, and this is because 001 is perpendicular to AB, since those two circles, okay. So that means that triangle A010 is similar to triangle BEC. And
now we can get similarity for AOO2.
And yeah. All right. CDB. And then we can use that.
Now what I did was AO by OO1
So,
equals BC by EC equals BC by BD because EC equal to BD.
and that's
equals AO by OO2, which implies OO1 equals OO2.
all right. And so, all right. Make some room here. And we also have OA is equal to OH. So yeah, let me think about this.
This firstly means that O lies on the perpendicular bisector of both of those.
Yeah, so O lies on the perpendicular bisector of both. Which that means it's an isosceles trapezoid. Yeah. But wait, not necessarily, because yeah, the fact that O lies on the perpendicular bisector of both doesn't by itself mean that's an isosceles trapezoid, right? We need one more piece of information. Yeah, if we showed AO1 equals HO2, that would solve it. We're very close, it feels like.
We know the angles AOO1. I think we can also try to find angle HOO2.
Yeah, because we know all the angles from the similarities, so it's like yeah, not only can we show that O lies on the perpendicular bisector of both, but we can show all these angles are equal. It has to be enough to solve it. So yeah, we can also show AO. Let's see. So AO01. Well, I guess what. Oh. Yeah, but A001 isn't, yeah, they're not congruent, but Yeah.
Can we instead try proving that O1, O2 is parallel to AH?
It is parallel to AH, right? Yeah. Let me make some room. Okay. So yeah, I don't think O lies on the circumcircle of A. Yeah, but
Can we mark the point of common point of AEB and ADC?
yes.
Yeah, that one. And let that be T.
Let this be point D.
T.
E. I'm sorry. I'll call it for P. I guess we
Yeah,
already.
okay. And we want to show that AP is perpendicular to both of the segments. Yeah, it's perpendicular to O1, O2 because of symmetry. We can try proving that AP is perpendicular to AH.
Okay. I think that might be just an angle chase. We want to show AP is perpendicular to AH.
And yeah, it seems that PDB is congruent to PEC.
DDP
Is congruent to PEC.
is congruent to PEC. Ah, okay.
That should imply PD equals PC. And so P lies on the angle bisector of A.
So I'm just answering Hakan. I don't think we showed AH is parallel to O102. We showed that O lies on the perpendicular bisectors of both AH and O102, but I don't think we proved they're parallel.
Yeah, I think this finishes it. We just need to show that PD equals PC.
Okay.
The congruency PDB equals PEC implies this.
Okay. So let's see. Yeah, I'm just thinking the best way to prove that congruency, probably by angle side angle, right? It's probably the best way to do it. I feel like, do we really need point P? Let me see if there's a way to do it without point P. Because we know maybe we do need point P. I'm just thinking for a second.
Yeah, PDB equals PVD equals PEC because that is cyclic.
Yeah.
And yeah.
Yeah, so we can show by angle side angle that they're congruent. So Okay, and then so that means that PB equals PE. So P lies on the angle bisector of A. And so that means that angle APH, angle HAP is 90. So and okay, so once we know HAP is 90, since we also know that the angle between O1, O2 and AP is 90. So that means that AH is parallel to O1, O2. And that means that AH02 O1 is an isosceles trapezoid. I'll say a cyclic isosceles trapezoid. Yeah, I'll write this out later. So since O is on, I'll just say since O01 equals O02 and OA equals OH, right? All right, and so that basically solves the problem because so that means that H lies on the three circles in the question. So I'm just going to make room for that last statement. All right. ABC, ADE, and A01, O2. All right, so I'm going to move on to the next problem. Thanks a lot for the help on that one. So here is our fifth problem. So let ABC be a triangle inscribed in a circle omega. And P is the midpoint of arc BAC. Whoops. The circle with diameter CP intersects the angle bisector of BAC at points K and L. All right, so oops. So we need to make it so that they intersect. All right, kind of like this. Okay, so it intersects at K and L, where K is closer to A. So this is K, and this is L. M is the reflection of L with respect to BC, all right? And we want to show the circumcircle of BKM passes through the midpoint of BC. So basically, if we draw the midpoint of BC, oh, it looks like, okay, GeoGebra just gave away that KLEC is cyclic, but we want to show that BKEM is cyclic. So, okay, so the angle bisector, it's going to pass through the midpoint of this arc. So let me delete some of the excess. And okay, so first, can we show that this circle is cyclic? So can we show that E lies on this circle? Is it obvious? So angle PEC is 90 degrees. Oh yeah, it is obvious because angle PEC is 90 degrees. So E is going to lie in that circle. Now we want to show BKEM is cyclic. Is L the orthocenter? No, L can't be the orthocenter. But I wonder if L is like the Humpty point or something. A triangle B. Let's see. So we want to show angle MEB is equal to angle MKB. But MEB, we want to show MKB is equal to LEB. I wonder if L is like the Humpty point. No, I don't think so. Oh, okay. We want to show angle LBE is equal to angle LKE. So LKE, wait, that doesn't sound right. Oh, I keep getting confused. Let me draw this circle. So we want to show the circle exists. But so we know, let me draw the orthocenter. Because we know that the reflection of the orthocenter lies in the circumcircle. We want to show that the reflection of this point also lies on the circumcircle. I mean that's another way to think about it, right? We want to show the reflection of L lies on the circumcircle of KBE. What is, So I think, let me try something here. I wonder if LG, I think if we reflect this point, oh, it lies on the circumcircle. Yeah, that should be. I mean, basically, yeah, I think it's the same as showing BGLE is cyclic. Whoops. Where G is the orthocenter. Yeah. So can we show BGLE is cyclic? So we want to show angle BGE equals angle BLE. So BG is perpendicular to KE. I think that might be an angle chase. We want to show BGLE is cyclic, where G is the orthocenter of BKE. We have to compute angle BLE. Let me try something. There's a couple ways that I'm looking at this. Does F lie on that circle? B, no. So angle BGE is 180 minus angle BKE. Which is angle BKA. Is triangle BLE similar to triangle BKA? I think we... Yeah. Can we show triangle BLE is similar to BKA? Maybe that's just an angle chase. Let's see. PE and F are collinear. Let me see. So angle BEL is what?
FC tangent to the circle centered at D?
Yes. Yeah, that's an easy angle, Chase. Yeah, if I can show triangle BKA is similar to triangle BLE, that would solve it. So angle BEL is equal to angle CKL. So CKL is equal to angle BAF. That's kind of interesting. But BAF is equal to CAF. So wait, that doesn't make sense. Wait, let's check this again. So that's 48. And oh wait, now they don't look similar. What am I thinking? But these angles were equal? 15.5, 15.5. But I thought these would then also have to be equal. What? Oh, I was wrong about that.
Is DLF cyclic?
Is what cyclic?
BLEF.
Oh no, I wondered that earlier. But we want to, but BGL and E. If we can show BGLE is cyclic, that would solve it. But yeah, BGE and F are not cyclic. So we want to show BLE is B. How could it not be that BLE is BKA? Hold on a sec. BLE and BKA. What am I missing here? Because BLE is equal to BGE. Isn't BGE 180 minus BKE? Oh, because AK and E aren't collinear. Ah, stupid me. Okay. So yeah, maybe it's not as easy as I thought to show that that's cyclic. So BG is perpendicular to KE. And EG is perpendicular to BK. So angle BLE, can we use that FL times FK is FB squared. That feels like it has to be useful, right? LBF is equal to LKB. That feels like it's probably useful. So from there we know LBF, and we could say LBE is LBF minus EBF. We want to show LBE is LGE. And LGE, that's the angle between LG and GE. Let's see, LKB is angle A over 2 minus angle, or it's angle A over 2 plus angle ABK. I think if we can show that BK and BL are isogonal, that would solve it. Yeah, exactly. Wait, if we know, are you saying, so LBF equals LKB. Does that prove they're isogonal, that LBF is equal to LKB? Okay, let me start writing some LBF. Okay. All right, I think we have enough to solve this. It's just a lot to remember. I'm just trying to organize it in my head. So I had it at one point. Now I'm just thinking it through again. BKF equals LBF. LKE equals LCE. And a bit more finishes. Okay, so I'm trying to show that BGLE is cyclic, right? Okay, let me write this out a little bit. So I want to show that so I want to show the angle that GB makes with GL is equal to the angle that or GB makes with LB is equal to the angle that GE makes with LE. But we have angle that GB makes with LB is equal to that's the angle that LB makes with KE. Now that angle I think we can calculate. Think about this. So yeah, if you guys have the rest of the details, feel free to write it out in the chat. I'm just trying to think about how this works. I forgot. I feel like I had it for a second, but I forgot how it works. So BLE is BLF plus ELF. Oh wait, I think I might have it now. Let's see. Angle BLE is angle BLF plus angle ELF, which is angle so angle BLF is 85.7. Okay, and that's angle KBF plus so I'm using some of the stuff that you guys mentioned. So that's KBF plus angle EKL. Wait, is that right? No, angle ELF is angle CKL. Is there a better way? Okay. Let me check the chat. All right, so BLE is 180 minus BK. All right, so Serdar has the complete write-up, so thanks for that. So I'm just going to copy it in. Let's see how well this works. All right, so BLE is 180 minus LBE minus LEB, 180 minus LBE minus ELC minus ECL. Okay. ELC is ELC. Wow, this is a tricky one.
PLC equals EPC.
Did you say P? I'm sorry.
EPC.
What is P? Oh, EPC.
This equals to FBC.
FBC. Yeah, EPC is FBC. Yeah. Okay. So ELC is EPC, which is FBC. Okay. And then ECL is EKL. And LBE plus FBC is LBF. Wow, this is very interesting. So, all right. Whoops. I'm gonna, yeah. I'm sure it could probably be shortened somehow. I don't know, or maybe not. I mean, maybe this is the shortest way to do it, but it is a pretty awesome angle chase. All right, so I'm gonna write it out from start to finish.
Actually, calling alpha beta is easier, but this is the formal way.
Okay, yeah, I'll just finish it this way. Okay, so P is already defined in the problem. So, all right, so P, E, and F are collinear. And angle, so so E lies on the circle with diameter E. Okay, and then I'm going to say let G be the circumcenter of triangle KBE. Yeah, actually, you know what? Yeah, we don't need point G. I mean, this really. Yeah, because once we know BLE is 180 minus BKE, then the reflection of L over BC lies on, yeah. So, okay, so what assumptions do we make here? So,
I think we had to use that similarity that we mentioned earlier. So let's see, BLE, it's 180 minus LBE minus LEB. ELC is LBE ELC is F. Okay, I'm going to insert a step here. So it always messes it up when I do it like that. Let me so ELC is EPC. So I'm just going to rewrite this, but as EPC. Okay, and EPC is FBC, and ECL is EKL. And so you really didn't make any assumptions in this angle chase. Like we didn't even use the power of a point trick that was used.
I used power of point.
Yeah,
BFE
okay.
squared equals.
So you use that LBF is equal to BKF. That's where you did use that power of a point, right?
Yes.
Okay. So let me write this out. So we had that. So FC is tangent to the circle. Okay. So I'm trying to remember how I proved that. I thought it was, oh yeah, because angle PCF is 90 degrees. So okay, so we have that step. And so that means FC squared is equal to FL times FK, which, where did I go from there? Or FB, I'll say FB squared equal to F. And that implies that triangle FBL is similar to triangle FKB. And from there, that's how we know angle EKL, LBF is equal to angle BKL. All right. And then we have that big long angle chase, which is the key to the problem. Very interesting. And so once we know that, I mean, this basically proves that
the reflection of L over BC lies on so if L prime, so actually they give you M in the problem statement. So angle of BME is equal to angle BLE, which is equal to 180 minus angle BKE. So that means that BMEK is cyclic. And that means that the circle BKM passes through the midpoint of BC. All right. I'm going to draw that in and move on to the last problem. All right, that was very cool. Okay, so we have a cyclic quadrilateral with circumcircle omega. We have a bunch of incenters, so I'm going to put A at the top here. Let's just do it something like that. All right. I don't want the diagonals necessarily to be perpendicular. Okay, so we draw the incenters of ABC, ACD, and ABD. What's wrong with that? Why won't it work? Oh, I need encircle. What the heck? Encircle ABC. Encircle ACD. Encircle ABD. So I is the center of D. J is the center of E, and K is the center of F, and E is the midpoint of arc DB. Where's my perpendicular bisector? Okay, so I don't want to make, I'm going to draw in some more lines later. So this is E. The line EK intersects this circle again at F. And we want to show CFIJ is cyclic. That's kind of interesting. Okay, let me check that that's correct. Yes. Okay, so let me draw in some more stuff. All right, it's kind of interesting. I should draw AC. Yeah. Sec, I'll be right back. This problem looks hard, doesn't it?
So I see someone else joined. What's your name? Debayu. Where are you from? Or you can just watch if you want, either way. He's from India. All right. All right, thanks for joining us. CFIJ. How should we start? So, what's a good way to prove those are cyclic? So we know angle JCI is half of angle DCB. We want to show that's the same as angle JFI, I guess. That seems like maybe the best way to prove this. So we want to show JFI is half of DCB. And E is the midpoint of, so we want to show JFI is DFE basically. F is the mixtilinear incircle. Yeah, because, oh, I can't believe I didn't even see that. Yeah, because it's where the line between the E and K meets. So yeah, it's the mixtilinear incircle point. I'm not going to draw the mixtilinear incircle, but I'm just, for now, but I'm going to keep that in mind because that might be the trick. Yeah. So does that make it obvious? I think that solves it very easy, actually. Because we just need to show, oh, actually, it's still not that easy. It's still hard, never mind. So we want to calculate angle JFI. Yeah, let me, you know what? Let me draw that circle. So basically what I'm going to want to do to draw it as short as possible, I'm going to try to do this. And that point, oh, whoops, that point, and I'm going to draw the circumcircle of GHF. That is my mixtilinear incircle. It's almost like the circumcircle, but it's mixtilinear incircle. Okay. Whoops, didn't mean to do that.
I think the condition we want to show that CFIJ is concyclic, extending CJ and CI to meet omega at say S and T.
Okay.
Then we can, if we show that SFAT is a harmonic quadrilateral, then that would imply the condition.
Okay. So we want to show, I guess the way I have it labeled, we want to show FLAM is harmonic.
Yeah.
So L is the midpoint of arc AB, M is the midpoint of arc AB. I don't think that can be true because I don't think Oh, maybe it is actually. So we don't even need point C. Basically, if we have triangle ABD and L and M are the midpoints of those two arcs, and F is the mixtilinear touch point, then we want to show FLAM is harmonic. So we don't even really need point C anymore, right?
If I remember it correctly, then I think it's a standard result about the mixed linear point.
Hmm.
Yeah,
Let's see if we can.
FGL and FHM are collinear.
Yes.
And maybe
So yeah,
we
that.
can use projective here.
Okay. So I'm just trying to think. So once we know that FLAM is harmonic,
Yeah,
how does that end up proving that FJIC is cyclic?
yeah, so I go by the property that product of opposite sides is equal for harmonic. So
Okay.
FL divided by FA equals FM by MA, and then I replace LA with a corresponding incenter. I replace LA by LJ.
Okay. So LA, you replace with LJ. So FL divided by LJ.
Should be equal to FM divided by MI. And because the angles are same, this implies these two triangles are similar.
Okay. So those triangles have to be similar. FLJ,
Yeah,
and that proves it. Ah, wow. I can't believe we got through all these. Okay, so I'm gonna write that up. Let's see let's first see how do we show that FLAM is harmonic. I think it's a well-known property. I'm just trying to think it through in my head.
I think we can take the figures to make the incircle some bigger.
Yeah.
Yeah. We can delete the points C, J, I, K, etc. because we can hide them for now.
Yeah.
Can we bring B a little lower?
Yeah.
Yeah, make it something like an acute triangle. Yeah.
Okay, so we want to show FLEM is harmonic.
Yeah. And it's also a well-known result that GK DF is cyclic.
Yeah.
And that AK is perpendicular to GH and GKH are collinear.
Yeah. Yeah, I proved that on my channel. That's actually how I ended up drawing this circle using GeoGebra. But yeah, I proved on my channel that GKFB is cyclic. Let's see how I can show that FLEM is harmonic. So yeah. So
I
project.
think we can project them all on the line AK.
Okay. So project through a. We can project. Yeah, which point?
We would need to add some points. A point where ME intersects AK and a point where LE intersects AK.
Okay. I feel like there should be an obvious. Let's see. What if we project on a GH? Because GK is equal to KH. So if we project through F on a GKH, well, yeah, then we get GKH.
wait a second. So we want to show FLEM is harmonic. If we project through F onto the line GH, we get G, K, and H, but it's not the point at infinity. I guess I'm a little confused. You can label the midpoint of arc BD and then project those points. But K, in order to project 4 points on a circle, you need to project through another point on the circle, right? Oh, okay. But you're saying, yeah. So I think I kind of see. Okay, so I'm gonna label the midpoint of arc BD. I'm gonna call it N. So yeah, you're saying like if you take F, L, E, and M and you project them all through K, you get B, N, D, and E, which is harmonic. So I haven't seen IMO Shortlist 1999, but can we do that? Like, can you, if you have 4 points on a circle, can you project through a point that's not on the circle? I guess I've never done that before, but is that just okay to do that? You see what I'm saying? Like I have E, L, F, and M. Usually when I have 4 points on a circle, I have to project through, oh, well, I guess the angles would all be the same. The angles between, Do you kind of see what I'm saying? Like, can we just project through a point that's not on the circle itself? Like that? I thought when you have 4 points on a circle, you have to project through another point on the circle. Is that true or no? Okay, so if that doesn't work,
I think I have a proof of this.
okay.
You can join LE and extend ME to meet AK at 2 points.
Okay. Okay, so
We would find AO by AK, AO by KO, and AP by KP from the triangles.
okay, so that would show that EA, EL, EM, EF is a harmonic bundle.
Yeah,
Wait.
that would do it, because we can show that OAPK is harmonic.
Yeah. Okay.
We
So,
can differently find those ratios. And I think there are 2 parallel lines here which help our course.
okay. Since we only have 10 minutes left, I'm just going to start writing this up. Let's see. But yeah, I wonder, like, why can't we project if A, oh, we want to show ALFM is harmonic, not ELFM. Is that right? But like, was our goal to show that ELFM is harmonic or ALFM is harmonic? I forget.
ELFM is harmonic.
Okay. So if we wanted to show ELFM was harmonic, then if I go back to, well, I guess I can't show it anymore. Okay. ALFM is what you're saying. Okay. Or I guess I'm confused because, like, I don't think ELFM is harmonic, because if it was, then I feel like we should be able to project through F onto the line GH, and F goes, or that would give GKL, but then we wouldn't get the point at infinity, I guess, is what I'm saying. Yeah, okay, it was ALFM, not E. Yeah. Okay, so yeah, that makes sense. Okay, so all right, so what was I thinking? Okay. So by a well-known theorem, F is the point of tangency of the A mixtilinear incircle. Let me call it omega. All right. And then so it's well known that FG and FH pass through the midpoints of arcs AC and AB. See video on my channel. All right. Okay. Now, basically, okay, so we want to show, so I'll just say FLAM is harmonic by
So yeah, I'm just gonna not show it for now, just because I want to finish writing out the full proof. So since FLAM is harmonic, yeah. So I'll have to check out IMO 1998 or IMO shortlist 1998. But basically, then so from there it follows that FL over LA is equal to FM over MA. And that means that FL over FJ is equal to FM over, let's see, what am I doing? FL over LJ is equal to FM over F over MI. This should be FL over LJ. And that implies that triangle FLJ is similar to FMI. That implies angle FJC is 180 minus angle FJL, which is 180 minus angle FIM, which is angle FIC. And that means that FJIC is cyclic. So yeah, I didn't go into all the details of proving that it's harmonic, but I mentioned it earlier when we were talking, so maybe the viewers will see that. All right, so we are out of time today, but thanks everyone for participating. This was a super awesome session. Yeah, today was super fun. So we really just ran through all the problems. So thanks for all your help. So for everyone watching, if you want to join this session, feel free to email me at mgreend801@gmail.com. I'll give you a link to our Discord channel where you can talk to other participants on this session. And feel free to like and subscribe. So I'm going to stop recording, but thanks everyone. Have a good one.